Login accepted.
Can you hear me? Okay. Hello, everyone. My name is Paweł Jurczenko, and today I will be talking about multi-threading on the JVM platform. A quick info about myself. I work as a senior software engineer at CompStak. We are a US-based company, and we are providing a data platform for commercial real estate business. We are using JVM primarily in our services, and specifically, we are using Scala language. And Scala itself is the language I have been using for the last 6 years professionally. Things I'm interested in are distributed systems, concurrent computing, which is basically the topic of today's presentation, and functional programming, which also fits really well to concurrency problems. So we'll also have functional programming in a couple of slides. How will this presentation look like? The presentation will have a couple of sections. And my purpose today is to show you a wide range of many different aspects when it comes to a modern multi-threaded JVM application. We will not have time to go into very deep details in any of these sections. However, at the end of the presentation, if you have any questions, feel free to ask them, or you can also try to catch me somewhere in the halls of the conference. Let's start by saying, how can we think about multi-threaded applications in the first place? And the way I like to think about them is to visualize them as a layered architecture, where we have a couple of layers, and each layer is built on top of the abstractions that are provided by the layer that is directly below. On each of these layers, we have a concept of a thread, which, depending on the layer, will mean something slightly different. At the bottom of this hierarchy, we have a physical hardware layer, where a thread is not a concrete abstraction. It's more of an ability to perform a sequence of instructions. A layer that is built on top of the hardware physical layer is the layer of the operating system, where a thread is a concrete abstraction. It's something that we can have references to, it's something that we can manipulate on. On top of operating system layer, we are building application thread layer. In case of the JVM platform, this is the layer of JVM threads. If on top of the JVM threads, on the other hand, we'll build another multi-threading abstraction, we call such layer a layer of green threads. And basically, nothing stops us from going even further into this hierarchy and create our own custom multi-threading abstraction on top of green threads, of course, as long as we have a use case for that. There are also two terms and two concepts that are tightly coupled with such hierarchy. The first one determines the way threads from the higher layer will be executed on threads from the layer that is directly below. And this is a concept of scheduling. We have two main types of scheduling. The first one is called preemptive scheduling, where the scheduler is in the full control of the execution. The scheduler is in the full control of when the CPU should be taken out from the thread. The second type of scheduling is cooperative one, which is basically the opposite. It's where the thread is in the control. It's where the thread has to explicitly yield CPU back to the scheduler. The second term defines the relation between neighboring layers, and it's called a threading model. We have three main threading models in modern software development. The first one is called one-to-one, which means that each thread from the higher layer will have its counterpart on the layer that is directly below. And this is the model that we have between JVM threads and operating system threads, which means that if we create 10 JVM threads, we will also have 10 operating system threads. The second threading model is called M2N, which means that M threads from the higher layer will be executed on N threads from the layer that is directly below. And this is the model that we usually have when it comes to green threads. In case of the JVM platform, this might mean that we'll be running, for example, 1 million green threads on top of 10 JVM threads. The third threading model is not available on this slide, but it's a M2-1 model, where M threads from the higher layer will be multiplexed and executed on a single thread from the layer that is directly below. And this is the model that can be found usually on platforms that don't have native support for multi-threading, for example, in the world of JavaScript. And I have started telling you about green threads. Let's stick with green threads for a while. What are they like in general? In general, they are threads that are managed in the user space instead of the kernel space. In case of the JVM platform, this means that green threads will be completely detached from kernel threads. They will be scheduled by a runtime library or by the virtual machine of the language we are using. Usually, but not always, there will be scheduled cooperatively, but we do have implementations of preemptive green threads, and the green threads that will be a part of the JDK itself in the future will be preemptive. But usually, in different languages, in different platforms, green threads will be scheduled cooperatively. And examples of green threads you could heard of are coroutines, which we have in Kotlin, are goroutines, which we have in Go, and fibers, which have many different implementations across many different languages. Why do we even have to think about another layer of multithreading? Why do we need such another multithreading abstraction? Well, in case of the JVM platform, JVM threads are quite heavyweight. They are expensive to be created, they are expensive to be managed, context switching is also expensive. They are also tightly coupled to kernel threads, and kernel threads are like scarce resource. So by introducing another level of multithreading, we can lower the costs of thread management because we can make green threads much more lightweight. And since they are much more lightweight and more fine-grained, they are able to use resources that we have in the hardware in a more precise manner. They can use those resources more effectively. And since they are detached from kernel threads, we achieve different semantics when it comes to blocking. Because from now on, blocking on a green thread will block the green thread itself, but this will not propagate as blocking of the underlying JVM thread / kernel thread. Since they are much more lightweight abstraction, we can have thousands or millions of green threads in a single application. And as I said, if we have a platform that doesn't have native support for multithreading, for example, JavaScript, we can create such multithreading abstraction using green threads. When it comes to concrete implementations of green threads that we have nowadays, we have plenty of them. This slide is not exhaustive in any way. Those implementations, in general, in essence, will be very similar. Like, semantically, they will be very similar, but of course, implementation details will differ. Outside of the JVM, we have, for example, Go routines in Go, we have Haskell threads in Haskell, and we have Erlang processes in Erlang. By the way, they are called processes and not threads because they don't share memory with each other. In case of the JVM platform, we have coroutines already in Kotlin. We have fibers, and we've had fibers for many years on Java with Project Quasar. And in Scala, we have 3 main implementations of fibers. We have Monix, Cats Effect, and Zio. And we will also have, on the JDK itself, a native implementation of green threads. We will have something called virtual threads, which will be introduced by Project Loom. And I would like to tell you more about Project Loom. But before that, before we dive deeper in Project Loom, we need to define one more concept. And this is a concept of a continuation. So a continuation is a sequence of instructions that might be suspended and resumed at some later point in time. If we combine a continuation with a scheduler, then we can talk about virtual threads. But we need implementation for those. We need an implementation for both the coroutine continuation and the scheduler itself. In case of the JVM, we've already had schedulers for many years. For example, we have a fork join pool, which can act as a scheduler for such a virtual thread. The missing part is that continuation. We need an implementation of continuations on the JVM. And this is where Project Loom kicks in. Project Loom will bring native JVM support for continuations. On top of continuations, in combination with schedulers, it will build a concept of a virtual thread, which will be like an additional abstraction to regular threads that we've known for many years. In our code base, they will have a look and feel of regular JVM threads. But in the runtime, they will have different semantics. They will behave differently in the runtime. As I said, virtual threads are example or an instance of green threads, which means that we get the semantics of blocking that will block the virtual thread only, and this will not propagate as blocking of the underlying JVM thread. Project Loom will also adapt JDK internals in the way that those internals will be aware that we have a distinction to regular, classic JVM threads and the new concept, a concept of a virtual thread. And depending on which thread actually is executing the method, a virtual thread or a JVM thread, the behavior of the method in the runtime will have different behavior, will have different semantics when we are executing our application. And let's see an example of that. Let's see an example of a method that is aware of that new concept. And this is the method thread.sleep, which all of you definitely know. And this is the implementation from Project Loom internals. So basically, the thread.sleep method will be aware that it might be executed by a JVM thread or by a virtual thread. If this is a traditional JVM thread, the behavior will be the same as we've had for many, many years. We will be blocking the JVM thread for as long as we want, basically, in the method. If, on the other hand, the thread that is executing thread.sleep method is a virtual one, we will have different behavior in the runtime. We will be having a non-blocking sleep. We will be blocking, of course, the virtual thread itself, but no JVM thread will be blocked for the period of time we are sleeping. We will have a fully non-blocking sleep, basically for free, like, of course, if or when Project Loom arrives. And basically, all of the internals of the JVM will be adapted in a way that will benefit from virtual threads, and in a way that those internals will be aware that we have that new concept. Unfortunately, there will be some corner cases and edge cases where the JDK will not be able to use virtual threads, but those will be like edge cases and corner cases, and most of the internals will benefit like directly out of the box of that new concept. What else do we gain by having that another layer of multi-threading? As I said, we mostly benefit by having that different semantics when it comes to blocking, which means that concurrency primitives that traditionally were completely blocking, for example, locks or semaphores, if being run on top of a virtual thread or green thread in general, they will no longer block on the JVM thread. And let's see an example of that. Of course, if the Project Loom is released, the existing JVM concurrency primitives out of the box will not be blocking because they will be running on top of virtual threads instead of the JVM threads, but we are not yet in the world of Project Loom. However, if we have a library that provides their own implementation of green threads, we already can use completely non-blocking concurrency primitives on the JVM. And I would like to show that in an example. In this example, I'm using a traditional Java concurrency primitive, which is array blocking queue. And what I'm interested in this example is how will this data structure behave when I'm trying to put an element into that queue in case the queue is full. And the API of that data structure allows me to do so in one of three ways. The first method is called add, and the method add, if the queue is full, will unfortunately throw an exception. And my applications, we are trying to write our applications in my company in a purely functional manner. And in functional world, we are not throwing exceptions. So this method is not ideal for me as a functional programmer because it throws an exception. The second method is called offer, which is also not ideal for me because it will return a flag. True if the element was added, or false if the queue was full and element wasn't added. This means that you will have to decide what should I do if the queue was full. Should I sleep and retry the operation? Should I retry like immediately, or should I try to have different semantics here and different logic? It's also not ideal. The third method is called put, which will block the underlying JVM thread until there's space in the queue again, which is also not ideal. We are blocking precious and scarce resources we have. But what if we have an implementation that runs on top of green threads and not directly on top of JVM threads? If Project Loom arrives, we will have that for array blocking queue like out of the box. But before that, we need to use some kind of a library. And for this purpose, I'm using one of the libraries that we have in Scala ecosystem. It's a Monix library, which is like a great concurrency-oriented library with a lot of cool concurrency primitives and concurrency utilities. And Monix provides an implementation of green threads in its internals. They are called fibers in case of Monix. And basically, when we are trying to put an element onto the queue, the operation will run on top of a fiber and not on top of the JVM thread. How will this example work in the runtime? So we are creating a concurrent queue, and we try to put an element into the queue. If the queue is empty or there's space in the queue, the operation will proceed like immediately. However, if the queue is full, the fiber that was trying to put an element will be suspended. The thread that the fiber was running on will be released to the thread pool, which means that that thread could be completely reused like immediately by a different part of our application. And then we will start asynchronous and non-blocking waiting for space in the queue. If or when, at some later point in time, there's space in the queue again, the fiber that was trying to put an element will be awakened. Some thread from the thread pool will be assigned to that fiber, and the operation will proceed. All of that, the whole processing will happen in an asynchronous and non-blocking manner. No JVM thread will be blocked in the process, even when we are waiting for space in the queue. And basically, every concurrency primitive you can think of is already implemented on JVM in a way that will provide completely non-blocking semantics for that concurrency primitives. I have been using such concurrency primitives for a couple of years already, but we need a separate library for that purpose. We will have that natively in some time, thanks to the Project Loom. But right now, we have to fall back to some kind of a library. I started telling you a lot about non-blocking in general. Right now, I would like to narrow that down to non-blocking I/O operations. Why do we even have to think about non-blocking I/O operations? What is the problem with blocking I/O operations? Well, the problem is that very often, if you will have blocking I/O operations in your application, you will also have a lot of threads, because otherwise you wouldn't be able to process like hundreds of users simultaneously, hundreds of transactions, requests, etc. And if we have a lot of threads on the JVM, then we have a couple of problems. The first problem is the memory consumption. A single JVM thread by default will require a 1 megabyte of memory, which means that if we'll have 1,000 threads on the JVM, we will require around 1 gigabyte of memory just for the sake of maintaining those threads. The second problem is that if we have a lot of threads, we will also have a lot of context switches. And if we have a lot of context switches, then we will have a lot of overhead. We will pay the price just for the sake of constantly switching the context between threads. The next problem is that if we have a lot of threads, then we will have a problem when our application is throughput-sensitive one. Because throughput-sensitive applications, like CPU-intensive operations or CPU-bound operations, don't like when you have much more threads than you have CPU cores in your hardware. So by having a large number of JVM threads, we are degrading the performance of such throughput-sensitive application. If we have a lot of context switches, we will also have a lot of cache misses, because we will be constantly clearing and populating cache values. Such application might behave like there's no caching at all, but in reality, it might behave even worse, because we will pay the price for the overhead. We will be constantly clearing and populating cache values, and it has a price, and we will pay for that. The next problem is that every JVM thread is a root of GC process. So by having a large number of JVM threads, we might increase the time it takes to garbage collect our application. And the last problem is that if we have a lot of blocking in our code base, we unfortunately increase the likelihood of having a deadlock in such application. So this is why we need to think about non-blocking I/O operations in the first place. Those are the reasons, basically. But before we dive deeper in non-blocking I/O operations, we need to talk about one common misconception when it comes to non-blocking I/O operations. And the misconception is that non-blocking I/O operations are about better performance of the I/O operations themselves, which is not true. Because in general, blocking I/O operation will be as performant as a non-blocking I/O operation, at least when we are talking about the I/O operations itself. And there are two reasons for that. The first one comes from physics. Like, regardless of the API type we'll be using, blocking or non-blocking, the operation will have to be executed like in a physical sense. If we are sending 1 gigabyte of data over the network, all of the bytes that are part of that 1 gigabyte will have to be converted into an electrical signal, and they will have to be transferred over the wire. And the API type doesn't change that. The API type doesn't change the physics. The second reason is that I/O operations at the lowest level are usually already asynchronous and non-blocking, because they are using CPU interrupts. So the question is, what is blocking then? Well, blocking is a thin abstraction provided at the level of the operating system, which means that non-blocking I/O operations are not about better performance of the I/O operations themselves, but they are about better and more precise, more efficient resources usage. And this might lead to better overall performance of our application, but this will be like an indirect consequence of using such non-blocking APIs. And let's see at concrete types of communications we can have in our application and non-blocking API possibilities here. When it comes to network calls, we usually don't have a problem with performing them in a non-blocking manner. Because A, they are supported well on operating system, B, they are supported well on the JVM, and C, we already have many implementations of such non-blocking HTTP clients on the JVM. For example, we have Async HTTP client, which is a very mature Java library, quite popular in Scala ecosystem. Spring Web Client, which is popular in the Spring ecosystem. And since JDK 11, we have a non-blocking HTTP client that is part of the JDK itself. So usually, when you would like to perform a network call in a non-blocking manner, usually you don't have a problem with that. In case of file-based operations, we do have a problem. The problem is that not all operating systems support such non-blocking file-based operations. And unfortunately, for many years, Linux didn't have good support for non-blocking file system operations. This, in case of Linux at least, this changed around 2 years ago, because in May 2019, a new kernel module called IO Uring was introduced to the Linux, but JDK itself is not yet using IO Uring, which means that if currently you have a JVM application running on top of Linux, you don't have non-blocking file-based operations available for your application. And Java New I/O package doesn't change much in this manner, because classes like asynchronous file channel are asynchronous, as the name suggests, but they are blocking. Like, under the hood, deep in the implementation, they will be using a thread pool, and regular JVM thread blocking will be involved. All of those problems affect not only the JVM itself, they affect other platforms as well. For example, libuv library, which is very often used in the Node.js ecosystem, is also affected by the exact same problems, which means that if you have a Node.js application running on top of Linux and libuv is involved in the process, you will be having a thread pool when you are executing file-based operations. And as I said, all of that might change because Linux, for 2 years around, has a new kernel module called IO-Uring, which solves the problem of non-blocking file-based operations on Linux. But JDK doesn't use it yet. But people who are behind Netty are already doing a lot of experiments with using IO-Uring directly on the JVM. So hopefully, in the future, we will have IO-Uring being a part of the API of IO-Uring being the part of the JDK internals. When it comes to communicating with non-relational databases in a non-blocking manner, we also don't have a problem usually because their drivers very often are already non-blocking and asynchronous. For example, we have async driver for Mongo, we have DataStax Java driver for Cassandra, and we have Lattice for Redis. And depending on what the non-relational database you're using, you probably also have a non-blocking client for your database of choice. So usually not a problem here. In case of the relational databases and communicating with relational databases in a non-blocking manner, we do have a problem. And the name of the problem is JDBC. And there are many problems with JDBC, really. Like, first problem is that it's quite old already. It's more than 24 years old right now. The second problem is that the API is completely blocking. The next problem is that the API is low-level and has a lot of leaky abstractions. And for me personally, as a functional programmer, the problem is that it has a lot of nulls, exceptions, side effects, things that I don't use in my applications. Like currently, my applications are completely free of nulls, exceptions, and side effects. So personally, I'm not a fan of such things in the API. However, if we forget about JDBC for a while, a couple of options arise. We have two types of solutions here, basically. We have low-level ones, which will be non-blocking, and they will have a look and feel of the JDBC itself. And we have some kind of high-level solutions wherein we will have a non-blocking communication with relational databases, but we will also get some kind of a DSL, for example, to interact with our database. When it comes to examples, generic low-level solution that we already have, by the way, generic, which means that it will work with many different vendors of the databases. We already have R2DBC, and we will have, when Project Loom is released, we will, for free, out of the box, have non-blocking JDBC. Because blocking JDBC calls that we've had for many, many years will be running on top of virtual threads. And such blocking call will be blocking the virtual thread only, and this will not propagate as blocking of the underlying JVM thread. But we have to wait for Project Loom to have that like natively. Generic high-level solutions, we have at least two. By the way, the list is not exhaustive as well. We have at least two solutions right now. We have Spring Data R2DBC, and we will have Hibernate Reactive, which is in development. And in Scala, we have two implementations already. We have Quill, which is working with Postgres or MySQL and provides a high-level DSL when you want to interact with the database. And we have a skunk library, which is like Postgres-specific. And I will show you an example of skunk in a moment, because I think it's like a super cool library. So I will show an example of that. In this example, I would like to show you how far can we go with being non-blocking and reactive in our applications, even though we are using a relational database. So in my company, we are working with real estate data. So we are working with a concept of a property a lot. So let's assume that we have a relational table with properties. And each time a new property is inserted into that relational table, we would like to execute some kind of a logic. For example, some batch processing, maybe. And what options do we have? How can we implement something like that? Well, the simple solution, let's say the traditional one, would be to use polling here. So every couple of seconds, we will be querying the database, and we would be asking the question, hey, have some new properties arrived since my last check? And such solution very often will work completely fine. I am using such solutions in many of my applications. because A, it's very simple to implement, and B, it's working. So very often, it will meet your requirements. However, sometimes we would like to react much, much faster than every couple of seconds. And such pool-based solution, when we are pulling the data out of the database, will not meet our requirements. Instead of such pool-based solution, we would be needing push-based solution. But can we have push-based solution in the world of relational databases? And it turns out that yes, we can, and I will show you an example of that. We need 3 ingredients for that. The first ingredient is that we need a way to react to a change in a relational table. And we've had such solution for many, many years in relational database world. It's called triggers. So trigger will be activated each time a new row is inserted into the database. The next ingredient we need is we need a way to push the data somewhere from the database. We're not yet caring about who will consume the data, but we just need to get rid of the data and push it somewhere. And we also have such solution in relational databases. In case of PostgreSQL, it's called channels. So we have 2 ingredients now. We have a trigger that will activate each time a new row is inserted. It will call a function, and the function will push a property ID to the channel. And someone at the end of the channel will have to consume the data later. And this is the 3rd ingredient we need. We need a way to consume PostgreSQL channels in our JVM-based application. But how can we do it? And for this purpose, I'm using Skunk library that I have told you about. And the reason I'm using Skunk is that it has, out-of-the-box, integration with PostgreSQL channels. You can use them right away. Skunk, by the way, doesn't use JDBC at all. Skunk is implementing raw Postgres protocol directly. So it's completely free of JDBC, which means that currently Skunk running on top of our JVM application is 100% reactive and non-blocking when it comes to communication with PostgreSQL. We start by creating a session, like a regular database session. We acquire the session, and we say that I'm interested in communication with channel called properties. And then I'm saying that, OK, I would like to start listening on that channel. Skunk will return us a stream of notifications right now. Stream comes from one of Scala libraries, which is called fs2 and is used for stream processing. And stream is a possibly infinite stream of data. And using reactive streams protocol, I'm also going directly from fs2 stream to project reactor Flux. In the end, I have a flux of notifications, which means that I have a possibly infinite stream of data that will be pushed by the database itself in the direction of the application. And in the process of waiting for the data, we will be 100% non-blocking and reactive. No JVM thread will be blocked in the process. So as you can see, even though we are using relational databases, we can go pretty far when it comes to having a non-blocking communication with those relational databases. We basically can have 100% of our application, regardless of the external subsystems we are using. We can have that in a non-blocking manner. OK, in the next section, I would like to tell you more about thread pools on the JVM. How many thread pools should we have? What kind of thread pools should we have? How many threads in those thread pools? I will try to answer all those questions. Let's start by saying that very often, if you have a simple application without strict performance requirements, a single global thread pool will be completely fine for the whole processing. I have many such applications. They don't require anything fancy. Like a single global thread pool will be doing completely fine. However, if you have a more complex application and you have some performance requirements about your application, such single thread pool based solution will not meet your requirements. In such cases, it's good to have at least 3 different thread pools. The first one will be used solely for CPU-bound operations. The second one will be used solely for blocking I/O operations. And the third one will be used solely for non-blocking I/O operations. Why the distinction? The distinctions comes from the fact that inherently all those 3 types of operations are completely different. They have different semantics. They have different runtime behavior, runtime characteristics. So we need to separate them. And we are separating them on the level of their thread pools. But what kind of exact implementations should we use for each of these? So in case of the single thread pool based solution, a fork join pool will be completely fine for our purposes. It's a very good general purpose thread pool, which works really well if you're mixing different types of operations on that pool, like whether they are CPU-bound operations, blocking I/O operations, non-blocking I/O operations. It works well when they are being mixed. But if you have like some strict performance requirements and you decide that you will go with the 3 pool-based solution, when it comes to CPU-bound operations, you have to answer 2 questions, basically. The first question is, how many tasks will I have? If you will have hundreds of tasks running simultaneously on that thread pool, it's good to have first of all, you have to be aware of the thread contention you might be behaving here. So it's not good to have a pool that has a single queue in the implementation, because your threads will contend over that thread pool. In such cases, it's good to have an implementation that has many queues in its internals. And for example, fork join pool has many queues inside, so you can use fork join pool in such case. The second question you have to answer is, are my tasks short running or long running? If they are long running, you shouldn't be using fork join pool. Why you shouldn't be using fork join pool when you have long-running CPU-bound operations? Because fork join pool, seeing such a long-running CPU-bound operation, will think that you are performing a blocking I/O call. And in reaction to that, it will add more threads to the thread pool itself. And as I said at the beginning of the presentation, throughput-sensitive applications and CPU-bound operations in general don't like when you have much more threads than you have CPU in your hardware. So by introducing more threads to your thread pool, which will be done by fork join pool, you are degrading the performance of such application. In such cases, it's good to have a bounded pool. A bounded pool when you have a guarantee that the pool will not grow, regardless of what's happening in the runtime. And you can, for example, use a fixed thread pool here. And the number of threads should be very close to the number of CPUs you have in your hardware. Sometimes it will be hard to answer those questions. In such cases, just prepare a couple of different scenarios and just benchmark them. Try to answer the question by doing a benchmark. Sometimes even after the benchmark, you might still be unsure what solution will be the best for my runtime. In such cases, you can think of, for example, canary deployments, where different instances of your application will have different setup of the underlying thread pools. And maybe the analysis you will be performing on the runtime data, on the production data, will answer your question, what exact thread pool and how many threads should I be using here? When it comes to blocking I/O operations, it's good to have an unbounded pool, which might sound scary, but please stay with me. I will describe it in a moment. And instead of limiting the thread pool itself, we will be providing limits at the higher semantic level. And I will show you a slide with an explanation of that. And for non-blocking I/O operations, a single small bounded pool will be completely fine. 1 or 2 threads should be completely enough for your requirements. And that pool should act solely as a dispatcher. It would work solely as an event loop in Node.js. It should be waiting for notifications from the operating system. And as soon as the notification arrives, you should be shifting your computations to one of those 2 other pools, to either pool for the CPU-bound operations or pool for blocking I/O operations, depending on what operation happens after your non-blocking I/O call. You shouldn't be doing any computations, any blocking I/O on that pool. OK, I said that for blocking I/O operations, it's good to have an unbounded pool. Let's assume that we have 3 different types of blocking calls in our application. We have blocking network calls, we have blocking database calls, and we have blocking file system operations. All of them, under the hood, in the internals, will use the exact same unbounded cached thread pool. And instead of limiting the thread pool itself, we will provide limits at the higher semantic level. For example, in the clients to those external subsystems we have. For example, in case of network calls, we can, in the configuration of the HTTP client, say that I would like to have at most 50 simultaneous connections. We are doing the same with database calls. We say that, OK, I would like to have at most 10 database calls. And the same for file-based operations. We can say that, OK, I would like to have at most 20 simultaneous operations. If the external subsystem we are communicating with doesn't allow us to easily limit the number of such calls, we can just use a semaphore. And if we are using a library that is providing their own implementation of green threads, we could have completely non-blocking semaphores, by the way. Effectively, after applying all those limits, we have limited the thread pool itself. We have limited it to 80 threads in total. But what is the benefit of all that? Why did we do it, basically? So there are 2 main benefits of that. The first one is that we didn't have to think about that number 80, like at all. We didn't have to calculate it. We didn't have to go over our application and see what exact numbers do we have in those fine-grained interfaces for external subsystems. We don't have to put that 80 number in the configuration, and we don't have to remember about changing that number each time one of those 3 intermediate numbers changes. So this is a huge win for me. We don't have to think about the application globally. We have to think only about those fine-grained external subsystems. The second benefit is that all of those operations, even though they are different in nature, are using the same thread pool under the hood. And it's a cached one, which means that if a thread is finishing its execution, it's not yet immediately killed. By default, it will not be killed for 60 seconds, which means that a thread that has just finished a blocking network call might be right away reused to perform a blocking database call or file-based call, which means that we are promoting reusage of threads in our application instead of constantly creating and killing them. So in general, this should lead to better overall performance of our system. And in the last section of my presentation, I would like to tell you more about asynchronous stack traces. And why do we even have to think about asynchronous stack traces? Why they have to be a part of the presentation? What is the problem with them in the first place? And I would like to show you that problem using an example. This is Scala code, but it's very simple code. And even if you haven't seen Scala before, you should be more or less know what is happening here. The future data type that is used here works in a very similar way to Java's completable futures. What do we have here? We have basically 2 methods. We have foo method and we have bar method. Both of them are synchronous. Foo method starts our asynchronous processing, and sequentially, after being done, it's calling bar method. And bar method fails with an exception. And in the main method, we are waiting for the result of our asynchronous operation. And what stack trace will we get in that simple asynchronous application? This is the stack trace. It's a pretty standard JVM stack trace. The exception is correct. The bar method was the method who failed with an exception. We have some noise from JDK internals, Scala internals. And there is one thing missing here in the stack trace. And the missing part is the foo method. By looking at the stack trace, you could get the impression that foo method wasn't involved in processing at all, which is obviously not true. It was involved. It was the first step in our chain of asynchronous calls. So even though our application is like simplest possible asynchronous application, we lost a very valuable information. We lost very valuable context information. You could imagine how much information do we lose when we have a complex asynchronous application. The question is, can we do something about it? And yes, we can. And there are many attempts to solve that problem. Some solutions try to solve that problem at the level of their operators, like at the level of the streaming. For example, this is what Project Reactor is doing with its operators. Kotlin tries to solve the problem at the level of coroutines. We also have a solution that is part of the IDE, which is IntelliJ async stack traces. And in Scala, we have 3 main implementations of asynchronous stack traces, and I will show you an example of one such solution. For this purpose, I will be using Cat's Effect library, which is also concurrency-oriented Scala library with a lot of great concurrency stuff. And basically, this is the same code we had, but I replaced Scala's standard library feature with Cat's Effect I/O. I/O is basically a description of asynchronous computation. That's all. We have foo method that starts the processing. We have bar method that will be invoked sequentially after foo method is finished, and bar method fails with an exception as well. In the main method, we are waiting for the result. And let's see what stack trace will we get if asynchronous stack traces are still disabled. Let's see that just for the comparison with the previous stack trace. It will be very similar. Like the exception is the same, bar method is there. We do have some noise from JDK internals, from library internals, and we don't have foo method. So nothing changes here, which was expected. But what if we enable asynchronous stack traces in the library itself? How will the stack trace look like? The stack trace will look like this. This is all, 3 lines of code. And there are a couple of things worth mentioning here. First of all, the exception is correct. It's the same that the method bar failed with. The second thing is that bar method was the method that has failed with an exception. We finally have foo method, which started asynchronous processing. So we finally have the missing information. We finally have the information about the missing context that we had. And the last thing is that we got rid of a lot of noise. We don't have JDK internals, Scala internals, library internals. All of that is gone. So the question is, how exactly does it work? How it's possible to have such stack trace? So basically, Cat's Effect has their own implementation of fibers. And as I said, fibers are green threads. And every possible asynchronous operation running in Cat's Effect is running on top of a fiber. And since Cat's Effect is in the full control of the execution, it's fully aware that fiber A called asynchronously fiber B. And in the process, in the runtime, Cat's Effect might propagate some additional information along the process. In effect, in parallel to creating a JVM thread level stack trace, we are creating in runtime, the Cat's Effect library is creating in runtime fiber level stack trace with like precise information of what exactly happened in our asynchronous processing. At the end, when the asynchronous processing is finished, basically the fiber level stack trace is replacing the JVM thread level stack trace, and this is what we get in the output. Basically, in the output, we get like very descriptive, very informative stack trace of what actually happened in our asynchronous processing. No information is lost. Every part of that chain is there. And we also got rid of a lot of noise, a noise that wouldn't be interesting to us at all anyway. So why bother with printing that on the console? And this is basically all I have for today. If you have any questions, feel free to ask them, but we have less than 1 minute, so you can also catch me somewhere in the halls of the conference, and I will try to answer your questions. And you can also contact me online, and I will be more than happy to have a chat and answer your question, of course, as long as I have the answer for your question. Thank you.